Continuing from our previous video where we talked about the relationship between the second derivative and the concavity of our curve, and therefore the shape of our graph, let's move on and let's take a look at these graphs of second derivatives. To be clear, these are graphs of second derivatives. This is not our parent function f of x. This is not the first derivative. These lines on here directly represent the second derivative. So I want to be really clear about that before we start. It's going to be like, Mr. Strike, there's no curve here. How are we having like an inflection point? Because like there's no curve. How is the concavity changing? That's not what we're graphing here. If this is my parent function, I'm not looking at a parent function here. I'm looking at a graph of the second derivative. So keep that in mind as we go through. For this exercise, we are told to consider the following graphs of second derivatives, and notice that only one of these represents a point of inflection at the point a comma f of a. Which one? So first of all, we're going to notice that my second derivative has a value of 0 at each of these points, and we know that when f double prime of a equals 0, there might be an inflection point. How do I know for sure? I need to test the values to the left and to the right of my a value. So let's start with our first example here. Our values to the left, as I'm approaching point A, are less than 0. Remember, this is a graph of the second derivative. So what this tells us is that in this region here, just going to draw the straight line through to help us visualize what's going on here. In this region here, as I approach from the left, all the values of my derivative, so f double prime of x, is less than 0. When this happens, we know that I have downward concavity, so concave downwards. Actually, let's be clear. Let's just be really specific. Which part is concave down? Because this graph is clearly not concave down. It's just linear. Therefore, we'll say the concavity of my original function f of x is downward. All right, what's happening on the other side of this line? What happens when my second derivative has a positive value? So moving on from this region right here, when f double prime of x is greater than 0, we know that it tells us something about the concavity of our original function. It tells us that the concavity of f of x is upwards. So we can kind of actually visualize our parent function for a moment. We know a little bit that until we reach point A on our graph, so x, y, point A, there's a lot we don't know, so this is a rough approximation. But as we approach from infinity to our A value, our graph is concave down, so it's curving downward. So I have, my frowny face. At point A, there's an inflection point, and after that inflection point, it is concave up. So I have my smiley face, and it's going to be curving upward. So my parent function is going to look something like that. And so do we have a point of inflection here? Yes. How do I know I have a point of inflection? Well, I can kind of roughly visualize it in my little sketch here. Or I notice that there has been a change in concavity. It's gone from being concave downward to concave upward. So, therefore, there has been a change in concavity. At our point A, comma, f of a. From downward concavity to upward concavity. So a f of a is an inflection point. And just to save time and space, I'm going to use some short forms here. All right, let's take a look at our next function. And once again, just notice briefly, I didn't mention this, but both of these functions are smooth and continuous. There's no gaps, there's no asymptotes, there's no weird features we're too worried about. We do notice that there's a sharp point here, so maybe that will matter. Let's see in a moment. So at this point, my f double prime of x does equal 0. So there might be an inflection point. I'm going to sketch the line just to help us visually split up what's happening here. And then let's consider what's happening to the left of the a value and to the right of the a value. As we approach that point from the left, what do we notice? All the values of, remember this is a graph of my second derivative, all the values are greater than 0. So we notice that f double prime of x is greater than 0. So the concavity of f of x is upwards on the right side of our point of interest. So as we now that we've passed our point where the second derivative has a value of 0, we notice that all my values are, once again, all my y values are greater than 0. So f double prime of x greater than 0. The concavity of f of x is up. And so what does that mean? It means that our concavity did not change. As we approached from negative infinity, it had a positive concavity. My second derivative had positive values everywhere. After point A, my concavity is still up. My second derivative has positive values everywhere. So therefore, this cannot be an inflection point because there's no change in concavity. Therefore, since concavity does not change, we know that, actually, we'll be a little more specific. Since concavity does not change at point A, then f of a is not an inflection point. Moving right along, let's start to learn how to use tables in order to analyze our function and quickly determine critical points, points of inflection, points of maximum and minimum, etc. In this example, so in order to learn this, we're going to work through a specific example and then extend out to general cases. For the function f of x equals 4x cubed minus x squared minus 3, determine a, the intervals of increase or decrease. So where is the graph increasing? Where is the y value going up? Where is the slope positive? And where is the slope decreasing? Where is the slope going down? And b, the locations of any maximum or minimum points. And tip, we're going to create a table to make our analysis easy. The first thing we can do is make a quick visual. I think I will, if I remember, pop into Desmos to show what this looks like, but I want us to predict without using technology first. So one thing I'll notice quickly is that this is a cubic function, so I expect it to have a shape something like this. And where are the places where my graph is going to change from increasing to decreasing? Well, if I come from the left, I notice that my graph is initially increasing, and then decreasing, and then increasing again. And there's certain points where it changes, and those points are going to be at my maximum and my minimum. And what do I know about those points? Those are points where my first derivative is equal to 0. And we may also want to look for points where the function or the derivative does not exist. So for example, if there's some kind of cusp or sharp point or asymptote. But this is just a pretty regular polynomial. It's a cubic function, and so the derivative will exist at all points. So let's describe briefly our steps, and then let's go ahead and do them. So basically step 1, I might not have too many steps here, but we're going to locate critical values. What are our critical values? It's going to be points where the derivative does not exist, or points where the first derivative is equal to 0. Note, like I said, because we're dealing with a cubic function, for a cubic function, there's no asymptotes or anything. For a cubic function, f prime x always exists. So this is the approach we're going to be looking at. We're going to find the derivative, set it equal to 0, and find those important points. One easy way to do this is going to be if we factor. Once again, Actually, we don't need to factor yet. We'll factor once we have our derivative. So locate critical points, and in order to do that, we're going to be, so we can call this like step 1b because it's still part of step 1. We're going to find our derivative. So let's go ahead and do that off to the side here so I don't get too cluttered. So I'm going to have my original function, f of x equals 4x cubed minus x squared minus 3. Let's find our derivative. This is pretty easy now. Remember just a few short weeks ago, we were using like half a page of limits to find derivatives. We don't need to do that anymore. We understand how that works, so we can take the shortcuts now. So my first derivative is going to be equal to 12x squared minus 2x plus 0, so I don't need to write that. So this looks pretty good, and just a tool to make my life a little bit easier. I could leave it the way it is, but I'm going to factor it. We're just going to take out a greatest common factor. So I notice that each term can be divided by 2x. I'm going to take out the 2x. So remember, divide all this stuff by 2x. It's a basic concept, but some of us still make mistakes with little factoring stuff like that, even in grade 12, so watch out for that. We're going to be left with 6x minus 1. And remember, I'm trying to find points where my first derivative is equal to 0, so let's set our derivative equal to 0 and find those points. So I'm going to set my derivative equal to 0. Now set f prime x equal to 0. So we're going to have 2x times 6x minus 1 equals 0. And hopefully you once again remember that in order for this to equal 0, either factor can equal 0. So either I can set this factor equal to 0, or I can set this factor equal to 0. And those are the only ways that this can have a 0 value. So I can do my calculations here real quick. 2x equals 0 happens when x equals 0. Or 6x minus 1 equals 0. 6x equals 1. X equals 1 over 6. So if I'm thinking back to my original graph, these are the points that are going to kind of break up my curve. So these are the points that help define or punctuate what our intervals are going to be. So let's define our intervals here. And I know this is a continuous graph. It continues to the left and right forever. So in my table here, the first thing I'm going to do is list my intervals across the top. So as I'm approaching from the left, I'm going from negative infinity up to my first point here, which is at x equals 0. That's what I just found. So my interval here is from negative infinity to 0. Then I'm looking in between my values that I just found here. So I'm going to looking in the interval from 0 to 1 over 6. And then I'm continuing onward. So I'm looking when x is greater than 1 over 6, or from 1 over 6 to positive infinity. Next, I need to choose a test value within each interval. This is a nice, easy part. So just choose some nice integer value that lies within our interval here. So I can choose any number I want between negative infinity and 0. And I'm just going to choose negative 1. It's a nice, easy value. What am I going to do with that value? Well, I'm going to plug it into f of x. So my first derivative, sorry, f prime of x, and I'm going to learn if the slope is positive or negative at that point. So I evaluate my function. So my first derivative function, which is right here. I'm just going to rewrite it off to the side here, just so we remember what it looks like. F prime of x equals 12x squared minus 2x, or alternatively, I could write it as 2x times 6x minus 1. So I plug in my test value. I evaluate this function at f of negative 1. And I don't really care about the actual value. I just care if it's positive or negative. So I will actually evaluate it here briefly. Let's take a look real quick. And if I evaluate this function, so f of negative 1 equals 14. But honestly, I don't really care about that. All I care about is if the value is positive or negative. So all I actually have to write here is a plus sign. And I could figure this out quickly or in a more indirect way as well without a calculator. What I could do is I know the two factors for my f prime of x. So together, these are my factors. of f prime of x. Honestly, I've never used this method. Like, I have never split it up like this to answer these questions, but you can. And I know if I plug -1 into this factor, I get a negative value because, 2 times -1 is -2. And I know if I plug -1 into this factor, it's also going to be a negative value. And so I know when I multiply these two numbers together, because they're both each factor, a negative times a negative is going to give me the positive. So I could have just predicted that way as well without actually evaluating and finding this number. Once again, I don't care about the actual values here. All I care about is if they are positive or negative. Next up, I need to, or let's see, what does this tell us about my function? Well, it has a positive slope, so I know the value of the first derivative is positive. So what does that tell me about the original function? Well, if its derivative is positive, that means the slope of the tangent is positive. That means that my graph is going up or it is increasing at this point or within this interval. All right, let's try this again. Let's take a look at our next interval. Remember, in our quick little sketch here, we're in our middle region here now. Once again, I can choose any value I want between 0 and 1/6. You can, so any number you want. Let's use 1/10 because that's pretty easy to work with. So x equals 1/10 or 0.1. And once again, we can do this a piece at a time. So if I sub x equals 0.1 into my first factor, I'm going to get a positive value. And if I sub x equals 0.1 into my second factor, I'm going to get a negative value. And I know that if I multiply a positive number and a negative number, because these are factors, then a positive times a negative is a negative. What does that tell me about my original function? It tells me that it's going to be decreasing at this point. And what do I know about a function when it goes from increasing to decreasing? What do I call the point in the middle here? Why, that's going to be a maximum. So there's going to be a maximum value at x equals 0. So we could even add like an extra column in here, but we don't really have to. I'll squeeze it in there just to show us, but it's not strictly necessary. All right, and let's move on. Let's see what's going on in the last half of our graph. So this portion right here where x is greater than 1/6. Once again, let's choose a test value, a nice easy number to work with that's greater than 1/6. Let's just use x equals 1. If I plug x equals 1 into my first factor, 2 times 1 is 2 is a positive number. If I plug it into my second factor, 6 minus 1 is a positive number. Remember, I'm multiplying these two together because they're factors. Positive times positive gives a positive product. So my function has a positive slope at this point. It is increasing, so this is an interval of increase. And if I were to sketch roughly the shape of my graph, it's going from decreasing to increasing. So what do we call this point there? It is in fact a minimum. So when x is equal to 1.6, I'm going to have a minimum value. So let's summarize in words what we've seen here and also describe the location of the max and min, and then we can quickly sketch this as well. Actually, we won't sketch it yet. We'll get there in a minute. We have to do a couple more steps on the next page. But let's summarize here. Let's make sure we've actually answered the questions. So we were asked to determine the intervals of increase or decrease for the function. So let's answer for part A. F of x is increasing. So what were the regions where my first derivative was positive? Is increasing at, once again, I'm going to use set notation because I'm comfortable with that, but it doesn't really matter which one you use. And I'm going to erase my picture here just because I need room for my answers. Therefore, f of x is increasing when x, element of the real, such that x is between -infinity and 0, or x is less than 0. And x is an element of the real such that x is greater than 1/6. Or you could just write at -infinity 0, and sorry, this is actually wrong. Yeah, no, it's fine. I got it right. And 1 over 6 to infinity. I don't really care which method of notation used to explain that stuff. When is it decreasing? F of x is decreasing at, or when x is between 0 and 1 over 6. All right, that's our answer to A. B asked us to give the location of any maximum or minimum points. So for B, there is a local max. So what does it mean that it's a local maximum? It just means that within this area of the graph, it's a point where I have a peak and then goes back down. And a local minimum is a point where I have a trough. And it's not the global maximum or minimum because the graph continues. And so the actual maximum value, it goes up forever. So it's going to approach positive infinity. The actual minimum value, it's going to go down forever. So it's going to approach negative infinity. But within the region that we're looking at here, where the interesting stuff is happening, we're just identifying the local maximum and the local minimum within there. I don't know if we talked about that formally in a previous lesson, so I want to mention it here just so we're clear. All right, so local maximum at, where does that occur? Well, we figured that out here. It happens when x is equal to 0, at x equals 0. And so we could find the actual point here. We could evaluate 0, f of 0, and find that that point is 0, -3. And local minimum at, found that here, when x is 1 over 6, we have our minimum. X equals 1 over 6, and we can evaluate and find that point 1 over 6, comma f of 1 over 6 equals 1 over 6, comma -325 over 108. And we're just subbing that into our function and solving. So I'm not going to show you how to do that. I'm just going to give you the values here. All right, hopefully that made sense. So this has told us a bit about our graph. We've located our maximum and our minimums. We have located areas where the slope or the slope is increasing or decreasing. So we've identified our intervals of increase and decrease. What's missing though? We've talked about using the second derivative to find points of inflection, but I haven't actually used it yet. So let's go ahead and do that on our next page. Continuing from our previous page, we're still working with the same example. So we're still working with the function 4x cubed minus x squared minus 3. And we're asked to determine the intervals of concavity up or down. So I know intervals of increase and decrease. I know when the slope is positive or negative, but I haven't determined when it's concave down or concave up, and I haven't located my points of inflection. In order to find those, I'm going to need my second derivative. And so let's take a look at our second derivative. Concave up and concave down will be when my second derivative has a value. We can show that here for a moment. Concave up, f double prime of x is greater than 0. Concave down, f double prime of x is less than 0. And points of inflection, they are possible inflection point. I'm just going to use my shorthand again. Possible inflection point at f double prime of x equals to 0. So just like before, we're going to have to start by finding our derivative, setting it equal to 0, and then examining what's happening at those points. Let's do that right away, and I'll do that off to the side here on the left. I had my original function, f of x equals 4x cubed minus x squared minus 3. I found my first derivative already in the previous question, but we'll do that again just real quick here. 12x squared minus x. Let's find our second derivative. That's going to be 24x minus 1. All right, and sorry, not minus 1. I made a mistake with my first derivative. So now let's fix it up properly right away. So I forgot to bring my 2 down here. So minus 2x, and then 24x minus 2. All right. I am interested in setting my second derivative equal to 0. So f double prime of x is equal to 0 is equal to 24x minus 2. It's really not proper notation to have two equal signs in a row. I'm going to do it anyway for the sake of space here, but I'm also going to point out that you shouldn't do it, and some other teachers might get upset if you do that. In order to set this equal to 0, I'm going to factor it. I notice quickly I can take a greatest common factor out of each term, and I'm going to take out a 2. So I'm going to have this is equal to 2 times 12x minus 1. I want to set each factor equal to 0. Well, I can only set this factor equal to 0 because 2 is always equal to 2. So 12x minus 1 equals 0. 12x equals 1. X equals 1 over 12. So something special is happening at 1 over 12. That's some part in my curve where something special is happening. So I'm going to examine as we approach from the left to that point, and starting at that point and continuing on to the right. So my intervals of consideration here are going to be from negative infinity to 1 over 12. I'm going to look what happens at 1 over 12. So I'm going to add an extra column here. And continuing on from 1 over 12 to positive infinity. And once again, just a quick reminder, these are the non-inclusive brackets. These are the round brackets. So these do not include the actual point 1 over 12. They're just very close to it. All right, once again, test value, easy. It's almost like a guess and check problem at this point. We're just going to choose some number that is easy to work with, that lies in the interval, and test and see what's happening there. So let's choose a value between negative infinity and 1 over 12, and let's choose 0. Let's list our factors that we're dealing with. Once again, this part is not strictly necessary. I've taught this course a couple times and never done this part, but it's still a helpful tool, so I'll still show you. There's no harm in it. 2 is always going to be positive. It's not affected by my x value. 12 times 0 minus 1 is going to be minus 1, so negative. Positive times negative gives me a negative value. And what does it mean when my second derivative has a negative value? It means that my original function is sad. It means my original function is concave down. Feeling down. All right, what's going on in my other interval? So let's choose some value between 1 over 12 and positive infinity. Let's just use x equals 1. Once again, looking at my factors, 2 is always positive. If I substitute x equals 1 into my function here, I'm going to get another positive value. Multiplying these two together because they're factors, positive times positive gives us a positive result. And what does that mean about our original function if our second derivative is positive? It means our function is happy. It means we have concave up. And what happens when I have a change in concavity? So if we're going from concave down, to concave up, a change in concavity means that I have an inflection point at this point. And just be careful, there are two criteria that need to be met. My function needs to be continuous. So there was no asymptotes or anything there. I know I'm dealing with a cubic function here. There's no asymptotes. There's no regions where there's a hole or anything. It's not a rational function. There's no disallowed values, so that's fine. And we have a change in concavity. So we've correctly identified a point of inflection on this graph. So let's make sure we've answered our questions here. So we were asked to indicate the intervals of concavity up or down and the location of any inflection points. So let's answer. Our answer to C is that, therefore, f of x is concave down at negative infinity to 1 over 12. Once again, it's up to you which notation you want to use to define that. I don't really care. And f of x is concave up at 1 over 12 to positive infinity. And question D, Therefore, there is an inflection point at x equals 1 over 12, and we can evaluate and find that point. So the actual point is 1 over 12, f of 1 over 12. Once again, I'm not going to show my work here. I'm just going to tell you that the answer is 1 over 12, comma, negative 649 over 216. And all I'm doing is taking my x value here and subbing it into my original function. And you are all capable of doing that, so I'm not going to show that work here. So let's zoom out for a moment. And I didn't write step by step for everything, but let's go back and talk about it really quick. So first of all, I wanted to find my intervals of increase and decrease and locate my maximum and minimum points. So I found the first derivative. I set it equal to 0. I made my wonderful table. I looked at some test values within each interval, and I determined what's happening in those intervals. When is my slope increasing and decreasing? And in between those intervals, did I have a maximum or did I have a minimum? That was pretty good, but I still needed to learn about the concavity and the inflection point. So I did some more work. I did the second derivative, and I found my second derivative, and I set it equal to 0, and I found out when that occurred. I used that to define my intervals of consideration. Using test values and the second derivative, I saw that I had concave down in one interval. I have concave up in the other interval, and therefore I had an inflection point in between. And so if I've correctly identified intervals of increase and decrease, the location of the maximums and the minimums, the location of the inflection point, and my intervals of concave up and concave down. And I think we should put that all together and sketch our curve. So I'm going to insert another page here, so to speak, and let's put all this information together. Actually, I think the easiest way is going to be to kind of squeeze it in on this page. So I'm going to erase this part that said factors of f double prime of x, still important, but I'm going to use that space and write a few things out. All right, I've quickly sketched my xy plane here, and I guess I do know the exact location of some of my points, but we'll kind of draw a rough sketch here. The first thing I'm going to do is locate my maximum and minimum point. So looking back at my previous work here, I know that there's a local maximum at x equals 0 and negative 3. So let's indicate that point here. So x equals 0 and negative 3. And that is a maximum. So my curve is going to be something like this. We'll sketch that in real... Actually, I'm not even going to indicate that yet. And there's a local minimum at 1 over 6 and negative 325 over 108. So 1 over 6. So local max and a local min. This is very slightly below. So this is going to be a little fine to sketch. That's okay. Approaching from the left, so from negative infinity to 0, my function is increasing. So it's going to be going up. From 0 to 1 over 6, it's going to be decreasing and going down. Actually, I'll draw this more out of the way for a moment. So increasing, decreasing, and increasing. And I know my maximum and minimum point, so I'm going to have a maximum in here and a minimum. What else do we know? I know I'm going to have an inflection point at 1 over 12. So that's going to be right in here. So this is really fine work, unfortunately. Maybe I should have scaled this a little bit better. And I know that as I approach 1 over 12, my function is concave up. So it's going to be concave down. So it's going to be curving down. And after the inflection point, it's concave up, so it's going to be curving up. So my function is going to look something like this. So inflection point, local minimum, concave up after that. Coming from the left, concave down, and then inflection point, so concave down. So my function should look something like that. And we could be more precise. We could find additional things like x and y intercepts, and we'll talk about that on the next page. But this is our rough graph. And let's take a look at Desmos and see what this function actually looks like. So I'm going to pause and switch my window over to Desmos. All right, we're in Desmos now. Let's type in our function. F of x equals 4x to the power of 3 minus x squared minus 3. That looks pretty reasonable to me. Let's zoom in and let's take a closer look. That looks about right. Where is our local maximum going to be? It's going to be here at 0 and -3. That's what we sketched on our graph. Our local minimum is going to be at, and that's our fraction, but in decimal form, 0.16 repeating, and just greater than -3. And my inflection point is going to be in the middle. And I don't really have a good way of showing that, but I'm sure there's a way to do it in Desmos, but I won't worry about it. Overall, our graph does look correct. If we compare, I can't really show it on the screen at the same time easily, but if we can compare, we can see that this does look very similar to, actually maybe I can switch back and forth for a moment. So our graph here and our graph here look pretty similar. They're in slightly different, I mean, it's sketched by hand, so it's not perfect, but we did a pretty good job. And if we had known things like x and y intercept, we could have made that even more precise. So let's move on. Let's take a look at our next page, and let's take a look at the overall process or algorithm I can use. Algorithm just means like a step-by-step process. So what is our algorithm or step-by-step process to accurately sketch a graph using the tools that we've learned about over the previous few days? This is a lot of text, but let's just take a moment and read through it one piece at a time and get a feel for it. And also, we don't always need every single step. So don't freak out. We've already worked through this. We've already done a lot of this stuff together. This is just putting it all in one process. Everything's all here and ready to go. This is Waterloo's general algorithm for curve sketching. And a note from Ms. Spring. Remember, Ms. Spring is the original author of these notes that we're using in this course. Ms. Spring's step 1 is to take some time to just look at the parent function. Just look at our f of x. Maybe you already know some things about this type of function. And step 2, it might be helpful to factor the parts of f of x if possible. This is a great guide, but we don't always need every single step. So keep that in mind as we go. Sometimes certain things become obvious or don't apply to the specific function we're looking at. So use this as a tool, as a guide. It's not a firm rule. Also, you are not locked into this particular order. For example, it might be easier to do step 1 after step 3. Why? Because if we know where the discontinuities are, then we know which values are not defined for our function. But let's take a look at our steps one at a time and let's see what's going on here. Once again, these are just a guide. You don't have to do every single thing, but this is a good general process to figure out how to sketch our graph. First of all, 1, find the domain of f of x, i.e. the set of x values for which f of x is defined. So what are the x values that have matching y values? And I'll just highlight these as we go to kind of check them off. Find the y-intercept, so set x equal to 0, and find the associated y value. Step 3, determine any discontinuities of f. If we're just working with a polynomial, we aren't going to need to worry about that. But if it's something like tan x or some other rational function, we'll look for any discontinuities. 4, find the x-intercept or intercepts. So set y equal to 0 and determine the x values that satisfy that equation. Question 5, explore the limit of f of x as x approaches infinity and as x approaches negative infinity. In other words, we're determining the end behavior of our graph. So you do this to determine whether horizontal asymptotes exist, and if so, whether y equals f of x approaches the asymptote from above or below. Step 6. If f of x is a rational function where the degree of the numerator is exactly 1 greater than the degree of the denominator, then find the oblique asymptote and determine how it is approached as x approaches positive infinity and as x approaches negative infinity. And let's just stop and review the steps on the notes on the side for a moment. As we talk about step 3 and 5 and 6, we're talking about horizontal asymptotes and rational functions. These steps will not be necessary for a polynomial function. Why? Polynomial functions are continuous everywhere. They don't have horizontal asymptotes. They don't have the degree of the numerator greater than the degree of the denominator because they don't have numerators and denominators. We could already do many of these steps in advanced functions, but steps 7 through 10 are our new calculus tools that help so much in sketching an accurate graph. So you've already done curve sketching, very similar to this, if you've already taken advanced functions, and that's where you would have talked about things like more detailed examination of horizontal asymptotes and oblique asymptotes. We're just going to kind of mention them in passing here. I don't think we're even going to do any examples with them. We might. I haven't really looked ahead, but generally speaking, I'm not going to ask you too much about those. Let's continue with our steps. So we've identified any asymptotes. We've talked about end behavior. Step 7, find any critical points where the first derivative is equal to 0 or the first derivative is undefined. So we've looked at that in our previous example a few minutes ago. Step 8, determine the intervals where f of x is increasing and where f of x is decreasing by checking whether f prime x changes sign at any critical point of f of x or at any discontinuity of f of x. If f prime x changes sign at a critical point, x is equal to c, then a local extrema exists at c, comma f of c, provided that f of x is continuous at that point. So in other words, if our first derivative equals 0 or is undefined, there's something special going on there and you should investigate it. Step 9, determine all points where the second derivative, f double prime of x, is equal to 0, or where f double prime of x does not exist, in order to locate the points at which f of x may change concavity. Remember, it's not a guarantee. That's why we do our table and our test points to make sure our concavity actually changes on either side of that point of consideration. If f prime x changes sign at a critical point, or sorry, I was reading here, but we're down here. All right, so find all the points where f of x may change concavity. Note this will include any points where f of x or f prime of x is undefined or where f of x is discontinuous, and we've looked at examples of that already in this video or the previous video. Step 10, by checking the sign of f double prime of x on the intervals determined by the points found in step 9, determine the intervals where f of x is concave up or the intervals where f prime x where f of x is concave down. Locate any points of inflection. So look at points where it's changing from concave up to concave down and vice versa. And finally, step 11, sketch the graph incorporating all of the above information. So once again, this is a lot. We've already done all of this though. It's just intimidating seeing it all in writing. But the point here is to explain every required step. And basically, even if you didn't know how to sketch a curve, but you knew about finding the derivatives and asymptotes and stuff, you could just follow this. This is our game plan for accurately sketching a curve without needing to use technology like Desmos, graphing calculators, etc. Finally, let's narrow this algorithm down a little bit for specifically working with polynomials, which is what we're doing in this course. If we're doing this live, I may or may not have a discussion with you and chat about this. Otherwise, I'm just going to kind of give you the answers here and let's discuss. So the idea here is we want to indicate which steps in the sketching algorithm will be necessary for a polynomial function. Circle them in red in the next slide and let's just talk about it. So if we want to go through this, let's see which parts are actually necessary and we'll highlight them in red as well as we go. All right, so Miss Spring's first steps are always a great idea. Look at the function, see what we know about it already, and factor the parts of the function if possible. We want to find the domain, because I always want to know where my function is defined. If it's something like a square root function, it's only going to be defined for positive values of x, so I don't even need to waste any of my brain power or my time thinking about negative values of x. I want to find the y-intercepts. I want to find the x-intercepts. I don't need to worry about finding any discontinuities because polynomials are continuous everywhere. I don't have any horizontal asymptotes, so I don't need to worry about that. I don't have any oblique asymptotes, so I don't need to worry about that. Step 7, find the critical points where my first derivative is equal to 0. So that'll be my maximum and my minimum points. Determine the intervals where f of x is increasing or decreasing. So that's just where my graph is going up or going down. And that's fine. Determine all the points where my second derivative is equal to 0. So once again, that's where I have a change. in concavity, concave up to concave down, or concave down to concave up. Check the sign in order to determine that my concavity changed, and therefore if it did, that point in between is going to be my inflection point. And finally, sketch the graph. Tip: using tables for steps 7 through 10 is really helpful. We saw that in our previous example, and it really is helpful. It's a really useful tool to get a feeling for what our function is doing and quickly using some test values. And I think that is about it. This doesn't apply to us exactly. I've kind of modified things a little bit. Just know that now is a good time to work on assignment 6 if you're working on this live. And it does involve our algorithm for curve sketching, which we saw in this video. I've actually combined 2 assignments together. There's still only 2 questions, but one of them involves curve sketching. One of them involves optimization. So if you are working through this in class and you have access to the assignment, we've now seen the algorithm for curve sketching, and we've done an example or a few examples in this video. So you can go back and work on this that assignment now. Also, handing it in as a single file makes my life a lot easier. When you send it to me as multiple pictures, I need to take time to download multiple pictures. I need to convert them to a PDF so I can write annotations and write feedback. And it just takes time. If it takes 3 minutes per student and I have like 30 students in this class, that's 90 minutes. That's an hour and a half of converting when I have hours of marking to do. So please make sure you're handing things in as a single PDF on time, on Brightspace whenever possible. And my version of this note also has a quick little note about how to ask good math questions. And so that's something I think I'd like to discuss here as well. So think of this as like a little bonus lesson here at the end of this lesson on curve sketching. How to ask good math questions. So when you are stuck, when you are learning something and aren't sure about what to do next, or you just sat through a lesson and you have some concerns, you're not quite sure, let's start with what you should not do. I don't get it. Well, what don't you get? Most teachers, and me personally, when I've gone through the lesson, I've taught it a number of times. I know what common errors are. I know common questions. I've tried to explain things in a way that is as clear as possible and that hopefully answers any possible questions you will have. It's not perfect. Of course, every person is different. Maybe you got distracted during part of it. Maybe I went too quickly in my description. Maybe there's something specific you didn't get. That's fine, but you need to do some critical thinking and think about, what do I not get? Do I not understand the question? Are there vocabulary words I don't understand? Is it asking me to perform some kind of calculation that I'm unsure of which formula to use? So let's kind of summarize here. What are the things I should do to ask good math questions? So first of all, I'm going to say consider the difficulty. What are you having trouble with? What do you not get? Is there a vocabulary word that you're not sure what it means, so you're not sure what to do? Are you stuck on not sure which formula or method to use? Because even in math, we're still using English. We're still, well, for us in this course, we're still using common language. So generally we know we have to calculate something, we have to solve something. We should have some idea of what the question is asking us to do. It's just the specifics that we get hung up on. Maybe I forget what it means to expand or simplify or distribute. And then that's the key word I want to focus on. That's what I want to figure out. Or maybe I know I need to expand, or I know I need to do double distributive property and I forget what's the process for that. That's something I can focus on. I can check my notes. I can ask my friend. I can ask the teacher. We also want to say, tell what you know. What do you know about this topic? You were just in class. You did just listen to the note. You do have previous knowledge about what we're talking about usually. What do I already know about how to make graphs? Or what do I already know about polynomials or about derivatives? Start with what you know and see if that can take you a little bit at least toward where you're trying to get. Maybe I'm a little confused about all this curve sketching stuff and finding concavity and whatever. but I know I need the first and second derivative. At least find those derivatives. Then we can discuss from there, how can I apply them to this problem? Tell what you've tried. You can say, Mr. Strike, I found the second derivative and I tried to set it equal to 0, but then I wasn't sure. It was like a quartic, or it was like a cubic function. I don't remember how to factor cubic functions, or I never learned. Then at least we have somewhere to work. I know what you've tried. I know what you're trying to do. I can confirm maybe, oh, you made a mistake. You don't have to factor a cubic function. It's actually quadratic. You just made a mistake here. Okay, easy fix. Or, oh, this question from the CEMC courseware is extra difficult. They do want you to factor a cubic function. Here's how to do that quickly. Next, tell where you're stuck. So once again, I don't get it. I'm stuck. I don't know how to do this. I promise you, you know more than you think you know. You're selling yourself short when you just say, I don't get it, or I don't know. Look specifically. Mr. Strike, I was able to find the second derivative and set it equal to 0, but I'm stuck finding the x values. Or I was able to find the intervals of concavity, but I can't remember, how do I tell if it's an inflection point or not? So try to be specific in your questions. That's actually the last point. Be specific. Once again, if you don't know, if you don't get it, if you don't understand something, that's totally fine. It's normal to feel confused. Confusion can mean that your brain is working and trying to understand the topic, and that's not a nice place to be, but it's normal when we learn something new. If you already knew all this stuff, we wouldn't be teaching it to you. You wouldn't have to take these classes. So having trouble is totally fine. Having questions is totally fine. And I'm begging you, please go ahead and ask questions in class. So many of your classmates have the same questions, and students never believe it when we say that, but it really is true. And I've had so many students say, I don't want to ask questions because everyone else already understands and I don't want to look stupid. You won't. And if you are looking at others and judging others who ask questions and thinking they're stupid, that's a really not a good place to be, because you have had questions at some point. You did not understand all this stuff. There's no shame in asking questions. So please feel comfortable. Feel free to ask the questions. Many other people in the class will also have questions. Not everyone understands everything except for you. It's okay to be stuck and to need some help. So ask questions when you need to. Just be specific as possible. Once again, just saying I don't get it, it doesn't help me and it doesn't help you. You are capable of self-reflection. You are capable of critical thinking and thinking, where exactly am I getting stuck? And so please consider the things that I've talked about here. Consider where your difficulty is. Is it a vocabulary word? I'm not sure what the question is actually asking. Is it part of the formula or the method? I know it says to like optimize the size of the box, and we'll talk about that in our next video or so. But I don't remember how to do optimization, or I don't know how to optimize this kind of shape. So maybe I can check my notes or do some quick research or ask somebody around me. What do I know about the topic? What have we learned? When you are talking to your classmates or your teacher, tell them what you know. Well, I know we're supposed to start with this, and I've tried this method. I've gone ahead and set the derivative equal to 0, or I've found the second derivative, but now I'm stuck. I don't know how to find the x value, or I found the x value. I don't know how to find the y value. So be specific. All right, thanks for coming to my TED Talk on how to ask good math questions. I know this has been a long video, so thanks for following along with our curve sketching algorithm. And as always, if you're watching this live in class, I am available in the chat, ready to answer any questions you have. Or if you're watching this later on YouTube, you're welcome to email me. Or if you're really watching this later on YouTube and you're not part of my class, you're welcome to post questions in the comments below. Thanks, everyone. See you in the next video.